Hi everyone, welcome to the another session on low power VLSI design. So in previous session we discussed about that one type of that is switching power dissipation that is comes under dynamic power dissipation. Now we are discussing another type in dynamic power dissipation, that is short circuit power dissipation. So before going to the dynamic power dissipation means the device is in the active states and the signals are changing its values. That is categorized into majorly three types: switching power dissipation, that is already we discussed in the last session, and the present short circuit power dissipation, and one more type is glitching power dissipation. So coming to this short circuit power dissipation, the short circuit power dissipation that occurs in the CMOS circuit. This is the diagram for CMOS inverter, and that will be occurring whenever both the PMOS and NMOS, both the transistors are conducting simultaneously during the switching transition. So those two are conducting simultaneously in switching transition. So this creating the temporary direct path from VDD to ground. So you can observe here there is a direct path is forming between VDD and ground. Because of this, maybe it will the unnecessary action, and because of this action it will dissipating the power loss. So in low power VLSI design, short circuit power dissipation becomes the significant whenever the input signal is, that is input signal transition is slowly changing its values. Because of this changing means here it is depending on rise time and fall time. Because of this rise time and fall time slowly changing its transition, it may be occurring both the transistors are conducting simultaneously. So here the short circuit occurs when the both negative and positive means NMOS and PMOS transistors are on. So here we can observe here this is a slowly changing its transition from low to high or high to low. So whenever there are finite rise and fall times at the input of the CMOS logic gates, there is a possibility of both PMOS and NMOS transistors are simultaneously on for a certain duration. At the situation only, there is a direct path is forming from VDD to ground. So the input transition is changing its values slowly from one signal to the another signal. In that situation, there is a possibility from connection directly from VDD to ground. So because of this short circuit, the power will be dissipated. That is, the power loss is occurring. This is called short circuit power dissipation. So the short circuit power dissipation takes place whenever the input voltage is in this range, means VTN less than Vin less than VDD minus VTP. Means if it is VTN means the threshold value of NMOS value is less than the input value, and the Vin value is less than the VDD, and also threshold value of PMOS. At this situation, the both the PMOS and NMOS transistors are on, and those are creating the conducting path directly between the VDD and ground. See here, this is the formula, average current formula. I mean, this is 2 into 1 by T. So here, we need to conclude that one particular time period, whenever both the on means these are indicating the one particular time period. So we are using this integrating formula between the time period. So that I mean value is 4 by T into integral T1 to T2 I of T. So here the T1, T2, T3, T4, those time period you can observe in this graph. Slowly it is changing its state from T1 to T2, T2 to T3. That is, it is moving to the low to high and high to low fall time from T3, T4 to T5 and T5 to T6. So in between we need to find out that current value. So that's why we are using integration. So Already we studied in VLSI design the formula required to operating the current in saturation region. So this is I of t equal to 4 by t into integral t1 to t2 and some voltage value. So just that I of t in saturation region, that will be substituted in this formula to getting that I mean value. So this is the short circuit power dissipation. And one more type present in the dynamic power is glitching power dissipation. This is the third type in dynamic power dissipation. So glitching power. So glitching is nothing but glitches are often occur when the paths are having unequal propagation delays, and those are converge at the same point in the circuit. So glitches occur because of the input signals to a particular logic block arrive at different times. Glitches is nothing but spurious signals. Those are occurred whenever the uh, input signals reaching a particular block at different time intervals. So these additional transitions result in the power dissipation, that is called as glitching power dissipation. So generally, while doing the power calculations, we are assuming the gates have zero delay. But coming to practice, the gates will have finite delay, and this delay will lead to the spurious, undesirable transitions at the output. The spurious signals that call signals are known as glitches. So if you observe in this diagram, if the inputs A, B, C are changing the values from 1012 000, ideally for zero gate delay. Ideally, we are assuming the gates are having zero gate delay only. Uh, the output should be remaining at zero. But however, considering unit gate delay at the first stage, the output O1 is delayed compared to the C input. So like this, because of that unit delay, that is O2 is depending on O1 output and O3 is depending on O2 output. Because of this waiting, the signals are having some delay. Because of that also, some extra transitions, it is releasing the power, uh, power dissipation. So for that, the remedy is if you are using the balanced realization of the gates, you can reducing the delay between the gates. Then you can reduce the number of transitions. Indirectly, you can reduce the power dissipation occurring at the signals. So glitching power is also the significant portion of the dynamic power if the circuits are not properly designed. Majorly, it is occurring while the circuits are not properly designed. So, if you are using the balanced design rather than the cascaded design, you can reducing the glitching power dissipation. So, the possible ways to avoid that glitching power dissipation is, that is minimizing the glitching power dissipation is um, using balancing delays by using the balanced realization rather than cascaded. One more thing is for highly loaded nodes, buffers can be inserted to balance the delays and cascade implementation can be avoided. So if you are using buffers in between the circuits also, you can possibly decreasing the glitching power. But if you are using buffers, here one more point is that will increasing the overall delay of the circuit. So majorly glitching power dissipation is nothing but the spurious signals occurring from input side to the output signal side when the signals are traveling it in its path propagating from input side to the output side because of unwanted transitions uh, waiting for the delays, the glitching power will be occurred. So these are called unwanted signals or false signals or spurious signals. Those are called glitches. These can be avoided by using the balanced realization or by using the buffers in between the gates. So overall, the dynamic power dissipation is categorized into switching power dissipation, short circuit power dissipation, and glitching power dissipation. So switching power dissipation means the capacitor is charging and discharging in its path. And short circuit power dissipation is whenever the input transition is rising from slowly to high. There is a direct connection from VDD to uh, yeah VDD to the ground. At that situation, the short circuit power dissipation will occur. And glitching power means it will be occurring in the propagating the signals from input side to the output side. That will be worked on by using the proper balance realization. So this is about types of dynamic power dissipation. Thank you. Static power dissipation we'll discuss on the next session.